Alright, welcome back to our last video on op amps in the electronics course. Now from the last video we looked at the gain of an op amp in terms of the frequency, and we saw that the gain decreases as your frequency increases. Now this was just one limitation of op amps. There are several other limitations, and one of the biggest ones that we've already looked at in the Intro to EE course is clipping. Now we know that we will have clipping due to the supply voltages or saturation voltages, Vs plus and minus, where in this case we had the saturation voltages, the magnitude of those will be greater than 5 volts, and our output only spans in a range of plus to minus 5 volts. But if we decrease these saturation voltages to plus or minus 3 volts, the new signal is here where we lost this dotted line. So this is clipping due to the voltage limitation. We can also have current clipping. Now, typically, you'll see the output current, I/O, that can saturate due to a maximum sink or source current rating, and that'll be given in the datasheet. So let's look at an example where we have this circuit given here below. We have our supply saturation voltages given as plus or minus 12 volts. Our resistor combination, we have R1 as a 1K, we have R2 as a 3K, and we're going to say from the datasheet that the maximum source or sink current is plus or minus 25 milliamps. So that's going to be this value right here for I out. Now let's say our input voltage is a function of T, and that's going to be equal to V1 cosine 2000 pi times T. Now if we're at a low enough frequency that in our Bode plot, we're kind of on that horizontal line that we talked about in the last video, what we would see is that the output voltage divided by our source voltage, Vt, that's going to be equal to 4. So we could say that our output voltage is equal to 4 times V1 cosine of 2000 pi T. Now we know from our saturation or source voltages that we're going to have voltage clipping at plus or minus 12 volts. So if we look at what the maximum input voltage can be, V1 max, that's going to be plus or minus 3 volts. And anything after that, we're going to get that voltage clipping. Now if we take the input to a magnitude of 3 volts, our output voltage is 12 cosine of 2000 pi T. And right here we can do a KCL where we're going to have some input current into that node, call it I sub O as we've been doing, and then we're going to define some output currents that look like this. Now in this configuration, our KCL says that the output current is equal to the current through the load resistor plus the current through R2, and that's simply going to be equal to our output voltage divided by RL, and that's going to be equal to our output voltage divided by R2 plus R1. So we're actually going to take this current here and say that it's the same current that's going through R1. So that being said, the maximum value for the output current, we can just look at the magnitudes here. So that's going to be 12 divided by RL plus 3 milliamps. And now we can start to look at the load resistor. So if the load resistor is a 10K, our maximum output current is really only going to be 4.2 milliamps. You could have a plus or minus in either direction. So we're still okay with our plus or minus 25 milliamp source or sink current. Just take a note of that. But if the load resistor is equal to 100 ohms, then that output current can be plus or minus 123 milliamps, and that's going to be much greater than what we can actually sink or source. So if we actually looked at what the limiting factor is for when we would have a 25 milliamp output for the output current, well, we can modify the equation up here, and we're just going to use the magnitudes, but instead of 12 volts, we're going to be seeing what the output maximum is at 25 milliamps to actually find what that output voltage is. So we can simply divide 25 milliamps by the value for our load resistor, R2 and R1. And if we keep our L, or our load resistor, at 100 ohms, our output voltage is about 2.44 volts. Of course, that's the magnitude. And then dividing that by the gain of 4 that we found, our input voltage is 0.61 volts. So in this example, we're not limited by voltage clipping, we're limited by the current. Now there's a third thing we want to look at, and that's going to be called the slew rate. Now the slew rate, which is denoted by SR, that'll be given in the datasheet. But we define that by the magnitude of the time derivative of the output voltage, and we say that that has to be less or equal to the slew rate. Now if we violate that term, the op amp again starts to get a little bit weird. We can have distortion in the output signal that doesn't look anything like our input signal. So generally we want to avoid that. So let's say our output voltage is 12 cosine of 2000 pi t, and obviously that unit is volts. If we take the magnitude of the derivative of the output voltage, we have this term here, which we can simplify to 24,000 pi, and the unit for that is volts divided by seconds. Now again, that needs to be less or equal to the slew rate, and most of the time the slew rate is given in the datasheet by volts divided by microseconds, so you may need to convert. Now we can also define a full power bandwidth as F subscript Fp, and that's going to be equal to the slew rate divided by 2 pi times the maximum output voltage. Now, the story doesn't end here with op amps. We still haven't even talked about the output or input impedances that much, the true input currents or output currents into the terminals. We talked about that a little bit, but really there's a lot more if you dive into a data sheet. Now, if we just look at these characteristics, we're only going to highlight a few of them. The first one's going to be the input resistance, and you can see, as we expect, that's quite high, 2 mega ohms. But you can actually have a minimum of 0.3 mega ohms, and there are several things that impact this, including temperature. Now, temperature doesn't really get talked about that much in electronics as it should, but we'll definitely get into what happens when temperature increases. Also, in one of the introductory videos, we talked about a common mode rejection ratio. We didn't even talk about this for op amps, but it exists and it's important, and we will definitely get to it later on. And then lastly, we kind of just want to highlight the slew rate. Here it's given as 0.5 volts per microsecond. Now, these are just three of the things. You can see things like the input offset current or the input bias current. Those are also important, but notice the units here are nanoamps, so oftentimes those will get overlooked. In extreme applications, those might be important, but if we want to look into those things, we first have to really understand semiconductors. And this course will give an introduction to some semiconductor components. It won't go into everything because that is a very detailed course that a lot needs to be known as a prerequisite for. But this should actually be okay for you to go out and design some basic electronics. Now, in the next video, we're going to look at a new component, and that's going to be the diode. We talked about the diode very briefly in previous courses, but now we're actually going to start looking at what it is, what it does, how it reacts. If you like this video and learned something, please like, comment, share, subscribe. Thank you for watching. We'll see you in the next video.